This is the next video for Year 2 differentiation, and in this video I'm going to look at differentiating exponentials. Now, before we start, we're just going to have a little bit of a recap on what we've done so far. So remember, we've used the chain rule to differentiate anything that's a function of a function. So if I have y equals 7e to the x, if you remember from last year, dy dx also equals 7e to the x. But if I have y equals 7e to the 2x plus 3, we can use the chain rule in order to differentiate that. Now, if you just remember that the 2x plus 3, the power is the internal function, and therefore, I can say let u equal 2x plus 3, so y equals 7e to the u. And also on this side, du dx will be 2, and on this side, dy du, not a dx then, dy du is 7e to the u. So again, if we use our chain rule, which is dy dx equals dy du times du dx, you get 7e to the u times by 2, which of course will be 14e to the u, and then if we put u back, you'll get 14e to the 2x plus 3. Now, of course, we were using the chain rule to shortcut. So let's just have a little look at some of the rules. Okay. So, and these are the ones, so the first two on the left-hand side are the ones you learnt. Oh, sorry, the two on the top are the ones you learnt last year. So if y equals e to the x, dy dx is also e to the x, because it's what we refer to as a self-differential. If y equals e to the ax, then dy dx is a e to the ax. Okay, now if the power on e is ax plus b, you've already seen an example of that above. When you differentiate, you get a e to the ax plus b. And of course, if you've got e to a power where the power is any function of x, you're going to get f dash of x e to the f of x. So it's really important you notice that when we differentiate e to the x, the original function is always part of the differential. So there's e to the ax, and here we've got e to the ax plus b, and here it's e to the fx, and there e to the fx. And I've just wrote a little extra one there. You can see if y equals ke to the fx, then when we differentiate it, we get k times f dash of x e to the minus, sorry, I don't know what's happened there, I'll just change that. Okay, so that's e to the f of x. Okay, so let's have a look at differentiating some of these exponentials. So again, if you look, now it's very similar to the do that we did before. Okay, so your power is your inside function, so you get dy dx equals, so it's 2e to the 5x, and then if you differentiate the inside function, which for an e is the power, you get 5, and therefore you're going to get 2 times 5 is 10e to the 5x. Now you can do it straight away, and this is one of the times where you probably can do the inside first. Okay, now the next one, again, notice, and I like to put brackets around my powers so I can see, so they stand out. So, dy dx, so 3e to the 4x, you'd write down the original e function, which is 3e to the 4x, and then you multiply it by the differential of the power. Okay, and then minus 6e to the minus 2x, and then times it by the differential of the power. So therefore, dy dx equals 12e to the 4x. Negative 6 times negative 2 is positive 12. So we get positive 12e to the negative 2x. Now, some of you might be starting to realise that you can do this straight away. You don't actually need that intermediate line. Okay, now the next one, again, notice that the internal function is the power. So again, we are doing a bit of dot like we did before. So we differentiate outside, so that gives us 2e to the 3x minus 1. Okay, and then we multiply by the differential of the inside, which is 3. So dy dx will be 6e to the 3x minus 1. Okay, and I'm going to bypass number 4. Just be careful. So number 5, again, notice that the power is now not linear, it's a quadratic function of x, but the same rule applies. So dy dx equals 4e to the x squared minus 3x. So you differentiate. Okay, so write the original function down, and then we need to multiply by the derivative of the internal function. You get that. Now, to tidy it up, dy dx, I'm going to get 2x minus 3 with a 4 on the front, and then e to the x squared minus 3x. Okay, right, so we'll just look at some harder examples now. So it's really important that when you are differentiating anything to do with e, every term is in the form ke to the f of x. So if it's not, then you have to force it to be. So we'll have a little look at this number 1. Okay, and in order to get each term in the form ke to the f of x, we need to multiply out. Now remember, when you multiply out same bases, you add the powers together. So this one, you're going to multiply these out. So you're going to get y equals e. I'm going to do it all in 2 bits. So it's 2x plus 3x minus 2. Okay, and then minus e to the 2x times by 1. Don't really need that. So this is y equals e to the 5x minus 2 minus e to the 2x, and then it's in the form that we can differentiate. Now I'm going to try and start speeding up. So if I differentiate e to the 5x minus 2, I'm going to get a 5 from the power, and I differentiate the power, and then I write this down. And again, if I differentiate the power, I'm going to get 2, so it's minus 2e to the 2x. Now, the next one, again, I've got to simplify that. Now, be very careful. Okay, and I'm going to write it out longhand so we can see. So remember, the term in the denominator belongs to both terms in the numerator. So we're going to get y equals 4e to the 5x over 2e to the 3x plus 6 over 2e to the 3x. Now if we simplify that down, 4 divided by 2 is 2, and e to the 5x divided by e to the 3x is e to the 2x. And then 6 divided by 2 is 3, and of course this e to the 3x that's on the bottom needs to come up to the top, so we make it negative, e to the negative 3x, and then we're going to differentiate. So dy dx equals, well here we're going to get 4e to the 2x minus 9e to the negative 3x, and that's what you get when you differentiate it. Okay, now at number 3, now just be careful, that power 3 has nothing to do with the 2. So what we're going to do is we're going to give the cube to the 3, and we're also going to attach it to the e to the 4x. So this is what we get. So it's 2 times 3 cubed times e to the 4x cubed. And that's the important thing, that 3 has nothing to do with the 2. Now we're going to simplify it. So 3 cubed is 27 times 2 is 54. And then e to the 4x cubed will be e to the 12x. Okay. And then when we differentiate, okay, so it's going to be 54 times 12, which is 648e to the 12x. Again, you can do it if you want longhand. This would be 54e to the 12x times by 12. 54 times 12 is 648. Now the last one is a double bracket. So we just need to expand that double bracket. So we need to do some expanding just so that we're simplifying. So we've got y equals, well, our first one is 3 times e to the x squared, and then minus e to the 7x. We've got a plus 3, and then we've got, now be careful here, it's e to the x squared multiplied by minus e to the 7x. Just sort that out. So it's 3e to the x squared minus e to the 7x plus 3, and then it's going to be minus, because it's a negative times a positive, and then we're going to add the powers, so it's e to the x squared plus 7x. Right, now we've got every term, so we can differentiate it. So here, this first one, it's 3e to the x squared times by 2x. The next one will be minus 7e to the 7x. Of course, the 3 will disappear when we differentiate it, and we get minus e to the x squared plus 7x multiplied by 2x plus 7. And then we're just going to sort that one out. So dy dx equals 6x e to the x squared minus 7e to the 7x minus, and I'm just going to put this bracket at the front, e to the x squared plus 7x. And that's how we differentiate exponential functions.